So we will always start with if, the input does a certain thing, and I know the system, what will the output look like? Every time I draw a little shape like this, what I'm drawing is something that is changing over time with an implied zero. So I leave out the axes and the decoration just for speed, and because most of all, I expect you to kind of recognize those shapes by now. What I expect that to mean is that I have some function of time that describes the behavior of the input signal as it changes over time. And every time I draw a curve like this, I imply that we started off at some initial steady state, and the output then underwent a change from that initial steady state over time and reached perhaps a new steady state. This is not guaranteed. Not all systems will reach a new steady state, but in the case of low order, kind of numerator-dominated or denominator-dominated transfer functions, they will typically be of this shape. And most of the real processes that we study will be stable. In other words, they will reach a bounded new value. And so this is the Rosetta Stone for understanding the thing that we are trying to do in this module, which is, in all cases, answer these hypothetical what-if kind of questions. What if that signal, because now you can elaborate on this, right? So you can say, what would happen, so this is maybe case 1, this is maybe case 2. Maybe you become interested in answering the question slightly differently, and you ask, like, what would happen if the input goes down instead of up? How would that, what would that response look like? What if the output varies in a periodic fashion? What would that output look like? And so on, right? So we're asking these kinds of questions, and we're thinking about the nature of the different kinds of inputs, and we're trying to predict in some way what the output would be. When we started, our initial work was almost all focused on understanding how to get that check mark in the box of the system itself. In other words, going from not knowing what the system equations are to going to knowing what the system equations are. So that's the whole of the first section, was just modeling these systems. Because my approach with this module has been to leverage your knowledge from earlier study themes to help you to understand the following study themes. In other words, if you look at the way that we've analyzed systems, you'll have recognized that we have a couple of running standard systems where we've analyzed the system and obtained these results in multiple different ways, right? So think about, for instance, the draining cup experiment, where we started out with a physical experiment of this draining cup, where we simply plotted data points, right? That was one version of answering the question, what will happen if I take my finger off the bottom of that cup, off the hole? What will that shape look like? So we've got experimental. And then we wrote down a set of nonlinear equations and lately we've been using linear differential equations to solve similar problems. Now, weirdly, I suppose it's a little bit of a shortcoming on my side, but I expect you to understand that this case that I drew here, this negative case, so the case where, and you should recognize that these initial results that we got from our experiment and from solving the nonlinear equations also matches the shape that I expect to see that first order response kind of shape, going from some initial steady state condition with zero outflow to a new steady state condition with outflow. And so you'll see that we get many of the same characteristics in multiple different ways. Further, actually, there's another part of this. We've got our experimental methods, we've got our nonlinear equations, we've got linear differential equations, and then we've also got the thing that's also quite important to me, which is just sketch-based methods or intuition. In other words, being able to predict what those things will do without doing mathematics. On the one hand, we're saying, in this direction, or actually let's say here, ease of calculation. In other words, I'm expecting you to be able to sketch these diagrams intuitively without doing any work in your brain almost at all. Because really what we're saying is that this is the direction of internal calculation. If I say, you are not able, I think none of us, not us personally or any of you sitting here, are able to solve large sets of nonlinear differential equations. We're always trying to answer this question, but I'm trying to connect. I'm trying to kind of look at properties of that system. That's a very poorly drawn magnifying glass, right? I'm trying to look at properties of that system and say, how can we identify properties of the system that will result in characteristic behavior of the output? So what are those kinds of characteristics that we observe in the output? We've seen that some systems respond in this kind of nice, slow way that we associate with first order systems or with high order systems with real poles. This is a characteristic, right? A nice, steady, non-oscillatory response when I make changes. How do I understand the link that links that output characteristic to the properties of the system? I have a couple of ways. I can think about the order of the differential equation. So in other words, I can locate myself here and ask myself just how many differential equations are there? What is the order of those differential equations? And what is the nature of the response that I expect? Once I've linearized these equations, it becomes significantly easier to reason about this, because when I have linear differential equations and I've Laplace transformed, I only have to think about the differential equations in the standard form. So reasoning about like that magnifying glass works better in the linear differential equation domain than it works in the nonlinear differential equation domain. It's much harder to predict what nonlinear equations. We hope that by linearizing these equations, we know that the intuition and the math becomes easier. And we hope that we're not discarding too much of the essential nature of the system. Given a certain set of inputs and a description of the system, can you predict what will happen when those changes happen? But there are associated problems that I call set pieces. And so one of the associated problems, for instance, is this idea of taking a compound input, in other words, some input that maybe looks like this, rewriting this input as combinations of these. This you've seen before. When we are dealing with nonlinear equations, we've got the nonlinear equations, but we're trying to make those easier to understand, and so we're trying to get to linear equations. There's the set piece of linearization. That's a procedure. It's not really, let's say, part of the theory, and much of it can be automated using the tools that we have. But I expect you to understand mostly the consequences of linearization, the fact that we are paying a slight cost in terms of accuracy to gain great advantage in terms of calculability and predictability. So set piece number 1 is input characterization, or like rewriting inputs like this. Set piece number 2 is this whole action of linearization. Another big set piece, which sadly I'm going to remove from the curriculum, I'm no longer going to assess it, is the Skorkenstadt half rule, but mostly because I'm just going to write that as a function into TB control. As I develop code that does these things, these set pieces are so unimportant to me in this module that when I find time, I write them into TB control so that you don't actually have to learn how to do that. In the same way that I don't expect you to learn how to do inverse Laplace transforms in any other way than looking it up on the table. I don't think that there's huge benefit in learning the procedure of linearization. I think there's great benefit in learning what linearization is. But if I could write a foolproof method of linearizing equations and I could just tell you tbcontrol.linearize, that's the final story, my life would be better. Now, with that in mind, there's a final set piece. Okay, so set piece number 3 was taking high order equations and rewriting them as low order equations. And if you were in yesterday's lecture, you would have heard me say the easy things to analyze are things that look like rational functions. The easy linear transfer functions are rational functions of S. But often we find that there are also exponentials. And those things are problematic, right? So those are not awesome. And in many cases, in order to use the automated tools, we're going to either approximate that exponential by a Taylor series or a Potter approximation or some of those, any of these kind of methods that take nonlinear functions or non-rational functions and approximate them by rational functions. Or we're going to ask ourselves, like, how much of an effect is that thing actually contributing at all? So for instance, very small delays are inevitable. Most of us can safely ignore that time. Right? So the best way to approximate dead time is just to ignore it completely. And if it's very small, that's a very good way. It's easy, doesn't really cost you much. So all of these approximation methods, and those are basically the 3 that we're going to be using. We're going to use Taylor series, we're going to use Potter, and we're going to use the Skorkenstadt half rule, which is tuned for step responses.